So it's a pleasure to welcome Drlica-Wagner, all the way from Fermilab, to give our KICP Colloquium today. Alex got his undergraduate degree from Washington University in St. Louis, and did his PhD at Stanford, working on the Fermilab experiment. And since that time, he's been the David N. Schramm postdoctoral fellow in the experimental astrophysics group at Fermilab, where he's also the co-chair of the Dark Energy Survey Milky Way Working Group, deputy PI of the Maglite Survey, and a co-PI of the BLISS Survey. These are all other projects using the Dark Energy camera. Alex actually wears a number of hats. He's also probably our first speaker who is a member of the Chicago Wildfire, a local professional ultimate frisbee team. And so I think we're going to switch from soccer to ultimate frisbee for our collaboration meetings. What? Oh, on Tampa, yeah. Right, we have two professional ultimate frisbee players in our collaboration. Sorry, there's one other thing. Oh, right. So the other thing about Alex, which I will assert, even though we're not 100% sure it's true, I believe it's true that Alex has discovered more Milky Way dwarf satellite galaxies than any other human. Even if it's not true, we will still assert that. He'll tell you. So, and that's the subject of Alex's talk today. He's going to tell us about the Milky Way's dark companions.
Thanks, Josh. Can everyone hear me okay? Too loud? Too quiet? Just right. Okay. Thanks for that introduction. So today I'm going to be telling you a little bit about the Milky Way's dark companions. And so specifically what I'm going to be talking about are very small, very dark matter-dominated satellite galaxies around our Milky Way. And a large fraction of the results that I'll be talking about actually were made possible by the Dark Energy camera on the Victor Blanco telescope here at Saratoga. So that's what the picture you see here is. Okay. So just as a brief outline of the talk, I'll give a very, very short overview of the dark matter problem. I think everyone in the audience, or almost everyone, has some sense of what I'll be talking about there. Then I'll spend a fair bit telling you really the story of our searches for dwarf galaxies over the last 2 years, and going back a little bit further to what people had done before that. And then I'll go through briefly some of the interesting results that have come out of these discoveries. And then end with a look forward to what you can expect in the future. So starting with the dark matter problem. So it would be remiss to start without a picture of Vera Rubin. And to note that this problem, the idea that when we look out at the universe, the matter that we can see is only a small fraction of the total gravitating matter, has been around for 85 years. In large part, the work of Vera Rubin and others really pinned this down from an astronomical perspective with the rotation curves of galaxies, where you can see that even though the stars fall off as you go farther out, the observed velocities of those stars, and then as you get farther out of the gas, continues to increase. And this is telling you that there is more gravitating mass out in the periphery of these objects than what you can see. And as time has gone on, we've narrowed that down. So at first you start with the stars, but as you look at other wavelengths, you can see the gas. You can also image the dust. And as you look out on the universe in general, you can add up all of the baryonic components of matter. And what you come to a picture of is a universe that is dominantly dark energy, and I won't be saying much about that at all in this talk. But in the matter component, it is it is about 5% ordinary baryonic matter, and roughly 26% of this non-baryonic dark matter. And this dark matter is observed on all scales, from individual galaxies to clusters of galaxies, to clusters of clusters and large-scale structure all the way up to the CMB. What I'm going to try and convince you is that even though we don't know what dark matter is, and this is a plot from Tim Tatum, possible scenarios for what the constituents of dark matter could be, microscopic constituents. So you could think of this as the electrons or the protons or quarks that make up dark matter. Even though we don't know what that is, by understanding the smallest galaxies, we might actually be able to tell something about the fundamental nature of dark matter. There are two specific avenues of attack that I'll take with these galaxies. The first is what has been conventionally called astrophysical probes. And so this is to test the cold and collisionless nature of dark matter using the smallest galaxies. And the other is indirect detection, which is to search for the possible standard model products that could come from an interaction of dark matter particles. So if dark matter could annihilate to produce quarks or other standard model products, or is not quite stable and could decay into standard model products, we might be able to see these signatures in regions of high dark matter density. So why specifically target the smallest galaxies? Well, there's one key aspect of that that's important both for astrophysical probes and for indirect detection. The smallest galaxies actually have the smallest influence from baryons. So these objects are by far and away dark matter dominated. But they're not completely dark matter, they're not all dark matter. There are some baryons in them, and this is important because if they were only dark matter, it would be very hard to find them, very hard to study them. So they actually live in this somewhat optimal regime where you have just enough baryons, just enough stars, to serve as tracer particles so that you can map out the dark matter content, but not enough baryonic activity to disrupt what you think the core features of dark matter are, the core influence of the dark matter. So from the astrophysical probe side, the smallest galaxies are also important because they're the easiest structures to disrupt if dark matter is warm, so it is not cold, or is self-interacting. So in this case, what you'd see, and this is a plot of the dark matter transfer function, you can think of this sort of like a power spectrum, as one of the parts of the power spectrum. What you see is that as you go to the smallest scales, as you alter from the standard lambda CDM, so lambda cold dark matter paradigm, for example, have dark matter be a semi-warm sterile neutrino, you can see a deviation from the predictions of the standard model. Similarly, when we look at indirect detection, the smallest galaxies are important because intrinsic astrophysical processes that could also produce high-energy standard model particles. So you have dark matter, you're trying to see the standard model particles that dark matter could produce. In the smallest galaxies, astrophysical processes that could provide a background that could confuse that signal are minimized. Right? You have few baryons, so that minimizes that. And also, the smallest galaxies are the closest to us. And this is largely an observational bias coming from the fact that you can't see very small galaxies far away. But it turns out that these are the nearest and best quantified regions of dark matter over density that we know of. So we actually know the dark matter content in nearby dwarf galaxies better than we know it nearly anywhere else. And so why do we need more dwarf galaxies? Why aren't the ones that we have enough to test these fundamental properties of dark matter? Well, on the astrophysical probe side, we're really trying to tell the difference between some standard model and some alternative model, and right now the error bars are really large on this. So the statistical error bars are driven by the number of small structures that we have, and right now we just don't have very many. So in order to distinguish these two models, we need more statistics. On the astrophysical probe side, on the indirect detection side, we have these contours here, and this is, I'll get into this a bit more later, but essentially from looking at other regions of high dark matter density, we see some excess emission of standard model particles beyond what the astrophysical models predict. That's not saying that we've seen dark matter, that's saying we've seen something we don't understand. Right now, if it were dark matter, we would expect to see the same thing in dwarf galaxies. Right now we don't, but we can't exclude all of the parameter space that's available to explain the signal that we do see. So in order to completely test the signal that we do see, we want to add more dwarf galaxies, which will increase our sensitivity to faint signals and actually push our sensitivity down below to the level where we can either where we can either detect or exclude a dark matter signal or a dark matter explanation for the signal that we see. So just to give a visual example of what I'm talking about, so here, these are simulations. On the left is a cold dark matter only numerical simulation. On the right is with warm dark matter instead, and these come from similar initial conditions, but changing the temperature of the dark matter. And you can see here that the number of substructures, the intensity of the image corresponds to the line of sight through the density squared dark matter here. So each of these small dots here is a dark matter subhalo. It's a clump of dark matter inside the larger dark matter halo of our galaxy. You can see that cold dark matter leads to a much clumpier halo than warm dark matter. And if we can observationally test which of these are Milky Way inhabits, that would tell us something, or could tell us something about the fundamental temperature of dark matter. But it would be remiss to go on without noting, and this goes through much of the talk, is that there is this strong baryon caveat, in that baryons can also disrupt the smallest substructures. For example, if you have a small dark matter halo with a bunch of stars in it, and those stars go supernova, they can actually disrupt or spread out the dark matter content in the halo in which they reside. So simulations are just now getting to the point where we can fully simulate dark matter and baryons at the same time. And so we're trying to really distinguish between models of what baryons can do and what a warm dark matter model would reveal.
What will simulate this processes?
So right now it is still pretty coarse. So you're not simulating individual supernova. You simulate sort of the bulk effect as an energy injection mechanism that comes on a specific time scale. Yeah. So I hope that that's some motivation for why we're interested in finding these darkest galaxies. So here's a little bit about the search itself. So this search has been going on in some aspect or another for nearly 80 years now. And the main takeaway point here that I hope you grasp or you come away from this with is that detectors are really driving discoveries here, right? So when we're talking about looking for the smallest and the darkest galaxies, how small is small? What's the picture that we should have in mind? So this is a plethora of galaxies, and this is to scale. And what you can see here is our Milky Way. It's not the biggest, it's sort of moderately sized on this scale. If we take the Milky Way and we had the ability to see actually the dark matter halo surrounding it in a cold dark matter paradigm, what we expect is a smooth contribution to a dark matter halo surrounding the Milky Way and a number of substructures, right, scattered around. And those substructures are what are going to host the small galaxies that we're looking for. And so now if we take the Milky Way and we blow it up, and to scale we plot the Large Magellanic Cloud, so this is the nearest neighboring satellite galaxy, and the Small Magellanic Cloud. To scale, you can see that the Large Magellanic Cloud is roughly 1/10 of the mass of the Milky Way. And if you look on the sky, if you ever go to a clear, dark sky location in the southern hemisphere, you can actually see the large and small Magellanic Cloud in the sky along with the swath of the Milky Way. And so we expect that the large Magellanic Cloud is hosted by the largest of the subhalos that we see in these simulations. The satellites that we're looking for are going to be the ones hosted by the smaller subhalos. So this search really picked up. The large and small Magellanic Clouds have been known about since before recorded history, as long as people could look up in the southern hemisphere. But the first additional dwarf galaxy, the first faint dwarf galaxy beyond the large and small Magellanic Cloud, was the Sculptor dwarf galaxy that was discovered by Shapley in 1938. And so this is a hand-drawn, I believe, plot of the positions of stars that he observed from his telescope, which were his 24-inch photographic plates. So this is the spatial distribution of the stars. This is what it looks like if you were to take an image with a moderately sized telescope today. So this is still photographic plates, but this is from the DSS, the Digitized Sky Survey. If you were to take those stars and look at them not in the spatial dimension, so as their positions on the sky, but instead to look at their color and their magnitude, so this is essentially the brightness of the stars, with the brightest stars on the top and the faintest stars on the bottom. And the color goes from blue to red, so this is hotter stars and this is cooler stars. What you would see is the stars in the previous image, also the ones belonging to the dwarf galaxy, follow this characteristic isochrone, so this characteristic template in color magnitude space. And this template is just coming from stellar evolution. So stars start off on a main sequence that runs diagonally along the diagram like this. As they age and hydrogen burning stops in the core, they move off the main sequence onto a red giant branch, and then move over onto a horizontal branch after that, and eventually die away as dwarfs. And so maybe a bit easier way to see this is from a video. And so this is looking at Omega Cen, which is a nearby cluster of stars / possibly tidally disrupted dwarf galaxy. What's happening in this video is we're first sorting the stars by color. So all the stars of blue color are moving to the left-hand side, stars of redder colors are moving to the right-hand side, and then we're sorting them by brightness. So moving brightest stars to the top, faintest stars down to the bottom. And what you end up with is an isochrone similar to the one that I showed you before, where this is the main sequence here, here's our red giant branch, and here's our blue horizontal branch. So the key takeaway from this is that we have two pieces of information when we're searching for dwarf galaxies. We have the spatial distribution, and we have this distribution in color magnitude space. And both of those are important for being able to find very faint objects. So using these tools and largely scanning by eye photographic plates between sort of the 1938 and right before 2000, the increase in the dwarf galaxy population had come sort of by ones and twos. In the early 2000s, there was a major shift in the way that people were able to do dwarf galaxy searches, and this was largely made possible by the Sloan Digital Sky Survey. So now you had very large area, very sensitive, very well calibrated data sets that spanned a large fraction of the northern sky. So now you have a situation where you start off with a population of stars, and most of these are actually foreground stars from the Milky Way. But if you then go and take these stars and you apply to them a cutout, a cookie cutter, that is matched to the isochrone that you're looking for. So this is an isochrone for an old and metal-poor stellar population, which is what dwarf galaxies have been found to be. So you apply this selection criteria, and the stars that you're then left with after after applying this color magnitude selection to your spatial distribution, look like this. And you can see that there's some overdensity of stars here, which if you then convolve by a spatial kernel of typical dwarf galaxy size, which is of order a few arc minutes on the sky, you can see that this overdensity of stars just pops out immediately. And so this allows you to now find dwarf galaxies that look more like this. And so this is not a trick image. The dwarf galaxy is here, but it's extremely difficult to see by eye. And that's in large part because the stars belonging to the dwarf galaxy are the fainter stars, and your eye is naturally drawn to the brighter stars. So it's easy to see how this kind of dwarf would be missed in scans by eye of photographic plates. But with that statistical technique, you're actually able to go and identify stars that are likely members of this resolved stellar population. If you then go and observe these stars with a spectrograph, so you're able to measure now the full spectrum of these stars and look at the individual elemental lines, atomic lines, and measure from that a velocity for each star, you find that the stars circled in green are all moving through space with the same radial velocity. That radial velocity is about 200 kilometers per second. And so that tells you that there's some kind of cohesive object here that's moving through space together. This also gives you a very important piece of information, which is coming from the width of this histogram. So if these stars are moving through space together, and they're not all at exactly the same velocity, then there's some dispersion to the velocity of the stars that are bound to this object. And how fast that dispersion is, how fast the stars are moving within this dwarf galaxy, is constrained by how massive the dwarf can be. Right? So let me say that again, because that was confusing even to me. The dwarf galaxy, the gravity of the dwarf galaxy is binding these stars. Right? So the harder the gravity from the dwarf is pulling on the stars, the faster they're going to move, and the faster they can move and remain bound. If the dwarf is less massive, then very fast-moving stars will escape it, and you won't see them as bound to the dwarf. So by measuring the width of this histogram, you can actually get a measure of the mass contained by this dwarf galaxy. And so after SDSS came along and this type of dwarf finding was pursued, what you ended up finding is a bunch of these very faint. So on the x-axis here, I'm plotting the I-band luminosity of stellar systems, and on the y-axis, what I'm plotting is the mass to light ratio. So the ratio between the gravitating mass, which you can measure from the velocity dispersion of the stars in a dwarf galaxy, to the total visible mass, so to basically the total light then corrected by an initial mass function. And what you can see is that the dwarf galaxies are going to very high mass to light ratios. So these are some of the most dark matter dominated objects in the known universe. These are mass to light ratios of hundreds to 1,000. So there's hundreds to 1,000 times more dark matter in these dwarf galaxies than there is normal baryonic matter. And this separates them from a class of stellar clusters, so these are globular clusters, which also inhabit the halo of the Milky Way, but essentially have very little, if any, dark matter. And essentially these globular clusters can be, the dynamics, the velocity dispersions can be completely explained by the baryons that we see. And so this led to the actual definition of a galaxy, which was proposed by Willman and Strader in 2012, which is that a galaxy is a gravitationally bound collection of stars whose properties cannot be explained by a combination of baryons and Newton's laws of gravity. So essentially, you're defining a galaxy in terms of its dark matter content. So after SDSS, you saw this rapid rise in the number of dwarf galaxies that were found. And unsurprisingly, this rapid rise was also exactly correlated with the footprint of SDSS. So all of the red objects are these ultra-faint galaxies that were found with statistical techniques. They were only able to be found in the area that was covered by the Sloan Digital Sky Survey, which is largely focused on the northern hemisphere. So this leaves a very large opportunity here in the south for new digital sky surveys. And that brings us to the Dark Energy Survey. So I think people are probably fairly familiar with the Dark Energy Survey. But it's composed of a camera, so the 570 megapixel camera that's mounted on the top of a 4-meter telescope. The camera is special because it has a very large field of view and a very fast readout time, which means that it can cover the sky very quickly. It has unprecedented red sensitivity due to thick silicon CCDs. This is not so important for dwarf galaxy finding, but is very important for cosmology. The group of people who have put this together are quite large and all awesome. So this is the Dark Energy Survey collaboration from a meeting in Michigan that we had a few years ago. You probably see many of your own faces in this awesome bunch of people. So here's a look at what the data that come down from DCAM look like. So this is the full moon to scale. This is the DCAM footprint, also to scale. And each of the individual points you can see sort of modeled on this footprint is a star. This is actually an image of the Small Magellanic Cloud. It's hard to find things that are large enough to actually cover the DCAM focal plane. The SMC is one of them, and it actually extends out here. So just a brief note on data quality. So DCAM is an amazing instrument. It gives you unprecedented sensitivity for very faint stars and galaxies. There's a lot of stuff in the DCAM data that you still need to take care of. So just for those astronomers in the room, you'll be familiar with a lot of these things. I spend a lot of my time working on this kind of thing, rejecting things like man-made satellites that cross the DCAM focal plane, cosmic rays, which will also leave you spurious signatures. Bright stars lead to ghosting patterns over the CCDs. Since we're covering such a large area of sky, we inevitably run into these bright stars, and we need to figure out ways to deal with them. And then every once in a while, you'll have an airplane fly right across your focal plane that you need to get rid of. So after you spend a fair amount of time working on that and getting your data processing working and getting your artifacts rejected, you can come out with your first, this is the year 1 internal data release to DES. The first thing we did was to just make a plot of the log of the stellar density as a function of sky position. Right, so this is just the very first plot you would make as soon as you have a new data set. What you see immediately are a few things. So this is the Large Magellanic Cloud. You can see it streams over into the rest of the DES footprint. You can see a number of small, so red is more dense over densities here. Many of these were known about before, but then you also see some overdensities here and here that were just completely unidentified. These are actually the first 2 dwarf galaxies that were identified by DES. Basically, you knew what it was within, 5 minutes of looking at this, and then really knew what it was within 6 hours of actually checking that you hadn't made a mistake. But not everything just jumps out of the data that easily, and so Keith Bechtel and I, so Keith was here a few years back, we were both gamma ray astrophysicists before we moved into DES. And so when we saw this problem of extracting a small signal from a large background, we immediately thought about likelihood functions because that's where we came from. So this is an optimization on the cookie cutter technique that I described before that was applied to SDSS. So rather than independently applying your color magnitude selection and your spatial selection, you can build a model that includes the spatial distribution of stars and the expected color magnitude distribution along with the initial mass function. So you know that there are more faint stars than there are bright stars. And so you can actually include that as an additional criteria in your dwarf galaxy finding. And you can include things that you know about the survey footprint. So there are still going to be some holes in the survey footprint, some non-uniformity in the depth, and you can build all of that into your model. And the output is that when you look at an image like this, and this is actually the most significant dwarf galaxy that's been found in DES, still not apparent by eye, but if you apply this likelihood analysis, you can tag the individual stars that are likely to be members of this dwarf galaxy, and you can assign them a membership probability, so you know how likely they are to be members. And this is important because the next step is to try and measure the dark matter content of this collection of stars, and to do that, you need to do spectroscopy, and spectroscopy is expensive, right? It actually takes a lot of time to get a spectra for each of these stars, and so you want to be sure that you are selecting stars that are members of the dwarf galaxy, because that's the way you maximize the information from your spectroscopic campaign. And so that's what we did, and again, the idea here is that from the peak in this distribution, this is one that's at about 60 kilometers per second. You can see that this is a group of stars moving through space together. By the width of this histogram, you can actually measure the dark matter content of this galaxy. And so the year 1 data were amazing and added this increase of 8 dwarf galaxies. But we were not alone in doing this. So the DES data, the images had actually become public at about the same time that the catalogs were released in the collaboration. And people outside the collaboration also realized, what a great opportunity this was to look at the southern sky. And so they actually came to us while we were in the process of writing up our results and said, hey, we have this paper that we analyzed all the DES data. And we said, oh no. And it actually worked out probably the best it could possibly have worked out. We coordinated the release of these 2 papers. They were independent analyses. They cross-checked each other. They had the same results by and large. There were some factors of 2 that came from the conventions that people were using that ended up making us scratch our head for a while. But these came out, and actually now, and I just met them a few months ago, many of these people are part of the DES collaboration. And so this all worked out as best as I could imagine. But it did really scare us about year 2 of the DES data. So in year 1, we waited for the full dark energy survey processing to be done. And because DES is trying to do really hard galaxy science, they put a lot of care into their processing. We, by and large, are looking at stars. We're doing something much easier. So we just, for the year 2 data, we just skipped the DESDEM processing, processed it ourselves, made our own catalogs, and did our own search about 6 months after we'd done the year 1 search. And that time we won. There's no one that came out at the same time. So, but by and large, you can see that DES is not alone here. There are other surveys that are also contributing dwarf galaxies. And so some of these are surveys like Pan-STARRS, which you may have heard of. It's based in Hawaii, so it doesn't have the full southern sky coverage that we do. There's also the VST Atlas survey, which is from Chile, but it doesn't have as wide sky coverage or as deep as DES. And there's a distinction that I'm making here between open circles and closed circles. So the open circles are objects that we found photometrically that appear to be dwarf galaxies, have the characteristics of dwarf galaxies, but which we don't have spectroscopy for yet. So we can't confirm the dark matter content. The closed circles are ones that we have spectroscopy for. We can confirm that they're dark matter dominated and therefore galaxies by the definition of galaxy. So the map I showed before showed a strong bias to the northern hemisphere, which is where SDSS was covering. We've now added this footprint, red footprint here, which is where DES covers. The color scale here, the gray scale here, is the stellar density. And what you can see are these red points are dwarf galaxies and dwarf galaxy candidates that were discovered in DES. You can see there's still a lot of opportunity here. So when I was telling you about the difference between open and closed dots, I was saying that we are still confident that the open dots are very likely dwarf galaxies. The reason that I said that is that from the photometric properties alone, you can plot halo clusters. So these are star clusters, they're dark matter core. And you can plot dwarf galaxies. Those are the spectroscopically confirmed dwarfs in blue. The globular clusters are in black here. On the y-axis is the brightness of the stellar system, so it's the integrated brightness of the stars. On the x-axis is the physical size. And so what you see is that the dwarf galaxies in general are much larger for the same brightness. And in other words, they're more diffuse. And so the objects that we're finding are populating this locus of galaxies and extending it down to much fainter absolute magnitudes into a regime where we're really running into objects that we're unsure of the classification. And again, that makes the spectroscopy really important. Unfortunately, these are some of the faintest objects, and the spectroscopy is the most expensive for them. So again, we're not alone. There have been many papers over the last 2 years that have come out with more objects in this dwarf galaxy locus. I'm just putting a smattering up here. And that's where we stand now. So there's a lot of opportunity, and there's been a massive expansion in the number of satellites that we've discovered. And so now I'm going to go into some of the details about those. Yeah, before I move on.
This binary classification.
Yeah.
I'm presenting it, it seems like it's more continuous, more dark matter. Is it related to the same kinds of
So that's a great question. So the answer is we don't know what we're going to find here. We believe that they are fundamentally, they have different formation mechanisms. We believe that the galaxies are populating primordial dark matter overdensities. We believe that the globular clusters are, seeded within the galaxy and collapsing from molecular clouds. But yeah, this investigation is yet to be shown. Okay, so to say a little bit more about the spectroscopy. So I was saying that spectroscopy is very important for measuring the dark matter content and confirming that these objects are galaxies. It also tells us the systemic velocity, so this is the bulk motion of the stars. This is very important for learning about the Milky Way environment and how the Milky Way was assembled. And I'll say a little bit more about that later, but you could imagine that you could find dwarf galaxies that are moving coherently through space together, which could suggest a common accretion mechanism. You also get chemical abundances from the spectroscopy, and from this you can learn about the star formation history of these dwarfs, and you get high-resolution spectra of individual stars, which can be used to actually learn something about the origin of the heavy elements. And I think you had a colloquium about that somewhat recently, so I'm not going to delve into it too deeply. So this spectroscopy is really being pursued by groups around the world, and over the past 12 years, more than 12 papers have come out on just the newly discovered dwarf galaxies using 6.5 meter telescopes and larger. And the Magellan telescopes have really been a leading contributor to this science, and Chicago in no small way has contributed largely to these results. I think at least 4 of these papers are coming using, in part, Magellan time from Chicago. So just a big thank you to the Chicago TAC for that. So just to tell you a little bit of what the spectroscopy looks like, so these are the spectra of 3 different stars of different brightnesses. What you're looking at is the calcium triplet here. So these are absorption lines from the calcium triplet. What you can measure from the offsets of the peaks of these absorption lines is the velocity of each star. And so you can see, I've put the velocities of each of these stars here. And from the integrated equivalent width of each line, you can get a measure of the metallicity. And so this is all, the metallicity is also important because what we found is that the dwarf galaxies are some of the most metal-poor systems, and they have large metallicity dispersions. And the reason they are able to have large metallicity dispersions is that they've undergone some stellar evolution, some supernova events, but they have enough matter, enough dark matter, to hold on to that supernova ejecta. That builds the metallicity dispersion. So we're actually measuring these line positions on sub-pixel levels, and one important part of these uncertainties is they include a systematic uncertainty that comes from instability of the instrument itself. And so that's necessary to take into account whenever doing this kind of precise velocity measurements. So one of the objects that we actually pursued with Chicago time was this Eridanus dwarf galaxy. So this is the most distant satellite galaxy that was found with TES so far. It's fairly compact, or appears compact on the sky because it's at such a large distance. It has a very high velocity dispersion, which means that it has a mass to light ratio of about 420 solar masses, so 420 times more dark matter than luminous matter. That puts it right in the middle of the dwarf galaxy locus here. If you look at analogs, now that you know with the velocity data, you know the systemic velocity of this object. You know roughly its mass, and you know its distance. So you can look for analogous halos in, say, the Elvis simulations and ask the question, for halos, for simulated halos that look like this one, are they on their first infall? Have they gone through one passage around the Milky Way, or have they gone through multiple passages around the Milky Way? And so it looks like from the Elvis simulations that this satellite is on its second passage, that it's most likely that it's on its second passage around the Milky Way. And that's interesting because it's at 370 kiloparsecs, so outside the virial radius of the Milky Way, but it has no active star formation. So it could be that on a single pass around the Milky Way, the star formation in this galaxy was quenched. Outside Eridanus 2, the galaxies you see in the field are often, almost always, star forming. So something happened to Eridanus that quenched the star formation history. Another interesting thing that you can derive from Eridanus 2 is that there's actually, in this, coincident with the center of this galaxy, and I've zoomed in here, you can see actually another very small star cluster. Okay? So you have this small star cluster in the middle of this large dark matter halo. And that can let you constrain some things about the properties of dark matter. So if the dark matter is made up of very massive compact halo objects, so for example, primordial black holes, if it's made up of multi-solar mass primordial black holes, those black holes will actually dynamically heat this star cluster and eventually evaporate it. Okay? And so from the existence of this star cluster, you can actually set constraints on the fraction of dark matter that is made up of these massive compact halo objects. And this has gained some interest because there is this small hole here between similar constraints that can be derived from wide binaries in the Milky Way halo and other constraints that come from microlensing events that you can also see in the Milky Way halo. So this sort of fills in this region here. So there's still a lot of work to do. On average, the weather has not been great for us over the past 2 years. And it's taken of order 2 nights for each of these filled circles. And there are a lot of open circles left to do. So the next topic is the indirect detection of dark matter. So the idea here is that your dwarf galaxy is a region of high dark matter density, those dark matter particles could annihilate or decay to produce standard model particles, which would then travel to you or your instruments here on or above Earth. Okay? So there's some jargon, I may let it slip out, that the J factor is, if I say J factor, this is the line of sight integral through the dark matter density distribution, but you can think of that as the expected signal strength of a dark matter annihilation signal in an astrophysical object. So I mentioned before that there is this excess of high energy gamma rays in a region that's rich with dark matter, but also rich in other astrophysical sources. This is the center of our galaxy. So this is our galaxy. This is an all-sky map of gamma rays coming from the Fermi Large Area Telescope. This is a zoom in on the center of our galaxy after subtracting off all of the emission that could be associated with conventional astrophysical models. So this is a residual that you're seeing here. This residual is spatially extended and has a peak at an energy of a few GeV in gamma ray energy. Okay. So there are many proposed solutions to this gamma ray excess. One of them is that it could be annihilating dark matter. Another is that it could be a population, an extended population of millisecond pulsars, which are also known to be gamma ray emitters. And there's a large literature on this. If you do choose to interpret this gamma ray excess as a dark matter signal, what it gives you is two contours in dark matter annihilation cross-section space. What you would expect from the thermal relic cross-section, so if dark matter were annihilating in the early universe to yield the density we see today, you would have a cross-section here. What we find are a set of contours, and the plots here are from different groups analyzing the same data set with slightly different techniques. Depending on whether you prefer your dark matter to be annihilating into B quarks or into tau leptons, you get slightly different preferred regions. But the bottom line is that this is by and large consistent with a fairly vanilla model of dark matter annihilation. However, the galactic center is an extremely complicated region. There are a lot of other ways that you could be producing this gamma ray signal. And so it's essential to be able to test this dark matter hypothesis in other regions where there's a high dark matter density, and preferably much smaller baryonic contributions. So the dwarf galaxies are just that region. So this is what a gamma ray counts map looks like around one of the dwarf galaxies. You can compare that to the gamma ray counts map in the galactic center, and you can see this is a much quieter region. So if you go and analyze gamma ray data coincident with the dwarf galaxies, you end up getting this constraint here, this black line, and you can see that it cuts below, and so that means it excludes many of these simplest interpretations of the galactic center excess. Unfortunately, there is more systematic error in these contours than is shown here, largely coming from the fact that we don't know what the total dark matter content of the center of our galaxy is very well. And so what we would really like to do is to push our sensitivity down by a factor of 5 or so that we can conclusively either detect or rule out this dark matter interpretation. And so we now have this large population of new dwarf galaxies. Unfortunately, we don't know the dark matter content of all of them because we don't have spectroscopy yet. But we can predict what we would expect the dark matter annihilation signal strength to be based on the fact that from dwarf galaxies that we have spectra of, we see that the mass within the inner 300 parsecs, so basically the central dark matter density, appears to be roughly constant over a large range of stellar luminosities. And so that means that you have basically the same dark matter luminosity, and that your flux is really just driven by the distance to the dwarf galaxies. So you can use that and you can look at each dwarf galaxy individually. And so the yellow and green contours here are, they are the 84 and 97.5% containment regions that you would expect if there was no dark matter signal. And what you see is that 4 of the new dwarf galaxies fall above, outside of this region. So they have 2.5, maybe 2 to 3 sigma local significance. But if you combine all of the dwarf galaxies together, you see that the combined analysis, weighted by the individual signal strengths, expected signal strengths, doesn't pass outside of the yellow region. And that when you combine this, you see that the limits get worse because you now have these new galaxies with some slight excess signal, but the overall significance is still of order 1 sigma. So this is something that we very much want to improve on in the future, but yeah, I'll leave it at that. So looking forward, there are 2 regimes that we really want to get into next. The first is that there's a large fraction of the sky that's still largely unexplored. The second is that there's a large region at very faint magnitudes that we haven't explored yet. We expect that a large part of this boundary in the surface brightness contour is a selection effect from the observations. So there's been a steady progress from SDSS to DES, and then DES itself is going to make a large jump forward, which I'll talk about in the next slide. And then in the further future, we hope to get out to LSST. So the dark energy survey, the initial discoveries used 2 years of data, but really this was just single epoch data. So we would take one exposure, and we essentially had the depth, the sensitivity that we could get from a single exposure part of the, for each part of the sky. But DES over the survey lifetime hopes to take 8 to 10 exposures over each part of the sky. And so this will increase your sensitivity once you can combine each of those exposures. And so by the end of the 5-year survey, we expect to be sensitive to the faintest dwarf galaxies over a 4 times larger volume. And this will be exceptional for deriving the abundance of dwarf galaxies, which is important for constraining the subhalo mass function. So constraining how the abundance of dark matter subhalos, the clumpiness of the Milky Way's dark matter halo. So the Milky Way Science Working Group is one of the first within DES to start making use of this year 3 data, and I'm really pushing them to do this. We're a really active group. If anyone here is interested in getting involved, come talk to me. We'd love to have you. And so we're leading the search for dwarf galaxies in the full DES data set. And then our real objective is to be able to derive the Milky Way satellite luminosity function, which should be able to tell us directly, well, should be able to tell us about the abundance of dark matter subhalos in the Milky Way. The next thing that's really exciting about the DES dwarf galaxy discoveries looking forward is that they're not isotropic. So if you look, and if you just divide by area the DES survey in half, north-south, you can see that 2 new satellites are above this line and 15 are below this line. And if you were just to naively look at that as a coin flip, right, this is a 3 sigma unlikely scenario of just flipping a coin up or down. What makes this seem like a very biased coin as well is that the Large Magellanic Cloud and Small Magellanic Cloud are located off the southern edge of the footprint. So the idea here is that this overabundance of galaxies could be connected to the Large and Small Magellanic Clouds. So we now believe that the Large and Small Magellanic Clouds are on their first infall into the Milky Way. And it may be that as they've fallen in, they've dragged in their own population of satellite galaxies, which has then been stripped by the Milky Way in the process. And so simulations of this suggest that based on the DES data, that there could be of order 100 dwarf galaxies spread across the sky at the sensitivity level that DES could expect. and that 30% of them, or roughly 30 or more dwarf galaxies, could have originally been associated with the Large Magellanic Cloud. And so this gives you then, if you want to test this hypothesis, it gives you a treasure map for where to look. So this, the contours here are essentially the probability per unit area of finding a dwarf galaxy coming from, that was originally associated with the Magellanic Cloud as a function of sky position. So you can see the DES footprint, it's a little hard to see, but it's in black all on this side, and it covers relatively little of the highest probability regions. So Keith and I saw this, and we said this is a great opportunity for another survey. So we proposed to NOAO for a program to cover the high probability region as best we could. We were able to get some funding from NASA because they're very interested in the dark matter indirect detection aspect of this. We put together a collaboration of what's now about 45 people spread across the world. And so the MagLight survey is now aiming, so it turns out that the galaxy passes right, our galaxy passes right along here, which makes it very difficult to find satellites in that region. So instead we're cutting across here and then wrapping around the Magellanic Clouds in a region of the sky here. And so from this we hope to be able to find of order 10 new satellite galaxies in an area that's a fifth the size of DES. And a lot of the work that I've been doing on this recently is preparing for scheduling our observations for the coming semester. And you can see this is an observation simulator that I've written that basically builds up the program that DCAM is going to follow. So when we're on the mountain, we can just load things and run from there. The first results of MagLights just came out a few months ago. And it's the first dwarf galaxy that we found is right off the edge of the DES footprint. It's only 11 kiloparsecs from the LMC, so it's possible that it may still be bound to the Large Magellanic Cloud. So the next step is to naturally expand to cover the entire sky with DCAM. So this is a plot of the sky coverage of DCAM currently. Marceli Soros-Santos at Fermilab and I helped write a proposal to try and expand this. So it's going to hopefully be a multi-year proposal to eventually cover the entire sky with DCAM. We're starting off with an area that's in gray here. The survey is called BLISS. It's the Blanco imaging of the southern sky. Again, we're in the phase now where we're furiously trying to plan the survey. Our first run is in early February. Here we now have 4 bands instead of just G and R, which we were using for satellite galaxies. And we have 3 different science drivers, which are somewhat complementary, but also somewhat hard to all schedule together. And these are dwarf galaxy searches, gravitational wave follow-up, and then also searches for this proposed new solar system plan. So the next step is the Large Synoptic Surveys Telescope. So LSST is coming along on the order of 5 years, and we'll be covering the entire southern sky every 3 nights. It'll be going much deeper than DES. So the single epoch imaging from LSST will increase the volume by a factor of 4. By the end of the LSST survey, we expect the volume to be increased by another factor of 60. And so that brings us all the way out to the virial radius of the Milky Way. So we should be able to detect the faintest satellites we see today out to the virial radius of the Milky Way with LSST. And so we've got some work at Fermilab ongoing on that. The DCAM data is really going to provide an excellent quick start to LSST, and dwarf galaxy science, as we saw with DES, is one of the earliest science projects that can be done with a data set. You really want sky coverage, you really want depth, and you can work around a lot of imperfections in the data as you go. So we expect, if we're here now with of order tens of dwarf galaxies, we expect to be at hundreds with LSST. One important point is that in order to get dark matter contents for these dwarf galaxies, we need 30-millimeter telescopes to do spectroscopy. We just can't go deep enough with the instruments that we have today. And so this is sort of my cartoon picture of where we'll be in 10 years from now. So this is now on a logarithmic scale. This is the dwarf galaxy discoveries. So this is the spikes largely from DES. By adding mag lights and bliss, we hope to eventually get up to 100 dwarf galaxies. Well, I guess 100 dwarf galaxies is here. And then with LSST, we hope to take that up to several hundred. This is really smooth. I expect that it will actually come much more jaggedly since data products sort of come out on yearly timescales. So LSST can do a ton of other dark matter science, and I'm not going to say much about this, but if you're interested in doing dark matter science with LSST, come talk to me. There are many, many probes, and we're starting to try and get organized now into some cohesive group that's specifically focused on understanding the fundamental nature of dark matter with LSST. I think that takes me to the end of my talk. So thanks for listening. I think it's been extremely exciting 2 years for dwarf galaxy discoveries. I think there are many more exciting years to come. I think they're going to really help us understand the fundamental nature of dark matter. So thank you.
Questions?
So, in order to estimate the mass content of the dwarf galaxy, how many stars do you need to measure? I mean, from the histogram, because I think I saw there are only 20-ish stars, but since you want to, you also need to assume isotropic, like orbit.
That's right. Yeah, so with 20 stars, you can do pretty well. And 20 stars, it takes you to sort of a 3 sigma detection that it is a dark matter dominated system. So it excludes the dark matter 3 hypothesis with 3 sigma confidence, a bit more. It is subject to some assumptions about the velocity distribution in the satellites. For example, that they're relaxed and that they haven't been kinematically disturbed recently. If you are interested in indirect detection, so dark matter annihilation, you of course get a better prediction on your signal strength the better you're able to measure the mass. And so if you're able to go to 100 stars, you can shrink the error bars on the dark matter content even more, and it becomes a more valuable test of a dark matter annihilation signal.
Okay.
So combining your findings and these baryon effects, so what is the status of the so-called missing satellite products?
Yeah, so this, so the missing satellites problem was the idea that in simulations, you find tens of thousands or more dark matter subhalos within the Milky Way halo. This problem was largely remedied by the ability to, by basically the fact that not every subhalo is expected to be populated by baryons. And so the gray prediction here was derived independently of DES, before DES, and made a prediction for if you took lambda CDM and took a certain prescription for populating subhalos with baryons, made a prediction for how many satellites DES should see, and you can see that we're right on track. And so it's true that it's possible that we don't find all of these satellites with the upcoming surveys and with LSST, in which case the missing satellites problem would arise again. But as long as we stay on pace here, essentially the conclusion is that it's solved.
questions, and that was one of them. Just related to that is not just the scale of the galaxies, but other scales as well. Whether the information that you have now is consistent with the predictions. The other question that I had to do with this observation on Eridani that you made, that the passage through the Milky Way might have quite star formation. It's a little bit counterintuitive. You'd have imagined the opposite.
Yeah.
So I'm wondering what thoughts you may have.
Right. So one idea is that you can actually strip the gas that's required for star formation as you pass. So the idea is that Eridanus is likely not passing that close to the Milky Way, so it's not going through the disk, right? But you could have, say, ram pressure stripping as you go farther away, right? Another idea is that Eridanus may have started its life pretty close to the Milky Way environment. So right on the border of where reionization from the Milky Way could have blasted the gas out of Eridanus before multiple generations of star formation occurred. So the answer is we don't really know. What we do know is that inside of Eridanus, all of the dwarf galaxies that we've seen, with the exception of the LMC and the SMC, which are much more massive, are not star forming. Outside of Eridanus, within 40 kiloparsecs outside of Eridanus, we start seeing star-forming galaxies and galaxies with large H1 contents. So it may be that Eridanus is special because of its its close relationship, a closer than average relationship to the Milky Way. It could have been the passage that did it, but one of the hopes is as we go deeper, we'll find more analogs right on this boundary so that we can better pin it down.
Other questions for Alex? Okay, and just a reminder, students are invited to come up afterwards, and let's thank Alex again.